Happy Thanksgiving. Enjoyed some time with family. Section 2.4 is where we're at today. We took that 2.1 to 2.3 test, and I have them graded. I didn't put them in because we still have 3 people that haven't taken them yet, so I can't put up the retake information until I get the test back from those 3 people, and then I'll put all of that up there for you. So section 2.4, again, going to feel like a lot of review today. We're going to be talking about the real zeros of polynomial functions, which you spent some time on in Algebra 2. And our objectives are going to be using long division and division algorithm, and use the remainder and factor theorems, use the rational zero theorems, and find upper and lower bounds. And really, I think the only one that we may not get to today will be finding the upper and lower bounds. We do have 3 days slated for this section because there's quite a lot for us to do just to see all the different types of problems that we could encounter as we're going through these. So we'll start off by talking about long division, which usually brings groans from people, and that's because you remember back in elementary school when this was kind of a tough thing for you. And so we have to think about how this process works. And we remember, well, we have 32 and we want to divide that into 3,587. And there's a lot of vocabulary that goes along with this that you didn't necessarily use a whole lot when you were in elementary school. But we have the 32, which is the divisor. That's what we want to divide everything by. The 3,587, that's called the dividend, and that's going to be underneath our division symbol. And then the answer that we get is called the quotient. And we know that already by working with some word problems this year and talking about words like sum and product and quotient and all of that. But we don't necessarily try to sit and figure out immediately how many times 32 goes into 3,587. What we do is we look at 32 and we start looking at individual digits as we look at our dividend, and we realize, well, 32 won't go into 3, so I can't work with that. But if I move it over one digit here and think of that as a 35, 32 does go into 35, it goes into it once. So I put a 1 up there, saying that I recognize that 32 times 1 is 32. And then what I do is I subtract. So 35 minus 32 is 3. And now again, I know 32 won't go into 3, so then the next part of this process was always to bring down the next number. The next digit in this case would be an 8. And then I realized, well, 32 can go into 38. It can go in there once again. So I write the 1 as part of my quotient answer, and I write down the 32, and I subtract again. And I get 6. 32 won't go into 6, so I bring down the next digit, which would be the 7. And then I realize, well, 32 times 2 is 64. So I can use a 2 this time and get 64 and subtract. And I have this remainder of 3. So my answer is 112 and 3, I'm going to write that over here somewhere, over the divisor, 32. Now when you first learned this way back in elementary school, the teacher first had you write the answer as 112 R3, which we now know is ridiculous. We're never going to write it like this at this level, but that was just a little baby step because division was hard for you. So the teacher said, all right, we're just going to write it like this. It goes in 112 times with a remainder of 3. But we're not going to do that at this level. What we do is we recognize that it's the 3 out of the 32 that we have for the remainder. Now, this doesn't work exactly the same way with polynomials when we're long dividing or when we're using synthetic, but it's very similar. So what we're going to do is step this up and say how would that process work if we are going to divide a polynomial, 3x cubed plus 5x squared plus 8x plus 7 by 3x plus 2? And this, of course, was part of our objective. We have to be able to do this division. So we'd still have our dividend. Oh, I don't know if I left enough room up there for my answer, but we'll give it a try. And we are still going to use a divisor. And we're still using that division symbol like we did in elementary school. And now our focus is the same as it was when we did this with just numbers. And that is, how do I get rid of just the first term? I'm not focusing on the entire polynomial at any point. All I'm trying to do is get that first term to be a match so I can get rid of it. So right now, I have 3x plus 2. And I have to multiply that by something so that I can get 3x to the third. I don't even look at the plus 2 back here because, again, my job is to figure out how do I get the first term to be 3x to the third. And I realize I have the 3, I have 1x, I'm going to need 2 more x's. So I will need to take x squared times the quantity 3x plus 2. And I do distribute it to everything. So this will be 3x to the third plus 2x squared. Now I know at this point we're supposed to subtract. But because it is a polynomial and because we tend to make mistakes if we don't change it to adding a negative, we're going to go ahead and change the signs on these and then just think of it as addition. So 3x cubed minus 3x cubed did exactly what I wanted it to do. That first term is now gone. That means my little x squared worked. So I'm going to put my x squared up here as part of my quotient, and notice I'm lining it up vertically with all of those other x squareds. So like I said, 3x cubed minus 3x cubed, it's gone. 5x squared minus 2x squared, or plus a negative 2x squared, is 3x squared. And then I do the same thing that I did when I just had numbers. I bring down the next term. Now I start over. I come back over here and I think, well, what I have is a 3x, and the plus 2 I can't do anything about, but I have a 3x and I need it to be 3x squared. So I'm going to have to multiply this by x, because 3x times x is 3x squared. So I distribute the x and get 3x squared plus 2x. Again, I know I'm supposed to subtract, but because we're talking polynomials, much easier to change the signs and think of it as addition. So 3x squared plus a negative 3x squared, or as subtraction. So this will be gone, which is great. It means my little x out here worked. I'm going to line that one up above all the other x's vertically. And then 8x minus 2x is 6x. Bring down the last term, which is a 7. And I come back over here and start again with my 3x plus 2. This time I need it to be a 6x, so I'm going to multiply by 2. And that will give me 6x plus 4. And again, I want to change the signs so that I don't lose anything. And 6x minus 6x is 0, so my 2 worked. I'm going to line my 2 up vertically with all the other numbers, constants that we have there. 6x minus 6x is 0, 7 minus 4 is 3, and now there's nothing else for me to bring down. So that means I have a remainder there. So I write it as plus 3, my remainder, over my divisor, 3x plus 2. And that's what we call the fraction form of an answer. And that's because we have our x squared plus x plus 2, which is the quotient, but we also have plus a fraction here, 3 over 3x plus 2, because this one did not go in evenly. We had a remainder. So that is long division, and that's a big part of our objective for today, is to be able to long divide, which it's not difficult, it's just you have a lot to keep track of, and that's one of the things that you have to get used to is in the tortoise and the hare. You need to be the tortoise when you do this and just slowly go through and make sure that everything's going to work out. Now, to check our result, to know that we're right, because something like that's going to be worth several points. There's a lot of steps in that. You take the divisor times the quotient, and then you add the remainder, and that better get you the dividend, what was underneath our division symbol. Now it says we're going to check this with the two division problems from the former page. So I remember that the first one we had an answer that was 112. And then it says once we find that, we have to add the remainder, and we should get back to our dividend. So our remainder on that one was a 3. So 32 times 112 is 3,584. And we have to add that remainder of 3, which gives us 3,587, which was our dividend. Now, it's going to look a little more complicated when we're talking about what we had for our long division problem with that polynomial. So we had 3x plus 2. We divided that into 3x cubed plus 5x squared plus 8x plus 7, and our result was x squared plus x plus 2 with a remainder of 3. So we do the same thing. It's just going to look a lot more, it's going to have a lot more terms because what we're doing here is using polynomials. So now we would take 3x times everything in the second set of parentheses, and that would give us 3x cubed plus 3x squared plus 6x. Then we take 2 times everything in the second set of parentheses, so plus 2x squared plus 2x plus 4. And then I don't want to forget about my little plus 3 remainder there in the back. So now let's see what we get. 3x cubed, it's the only cubed term we have. Then we look for the squareds, plus 5x squared. Then the x's, plus 8x. And 4 plus 3 is 7. And we go back and look at the problem, and we see that our dividend was 3x cubed plus 5x squared plus 8x plus 7. So we can check it. And what we're doing when we're going through this process is using what's called the polynomial form of our quotient there. And so basically it's just like what would you write down if you were going to check it. So for today's homework, they're going to ask you for fraction form. They're also going to say, hey, let's put polynomial form down. This is the one that we put down if we're talking about polynomial form here. So the division algorithm for polynomials says let f of x and d of x be polynomials with a degree of f greater than or equal to the degree of d, where d of x is not 0 because, of course, we're dividing and you can't have a denominator of 0. Then there are unique polynomials q of x and r of x called the quotient and the remainder such that f of x equals d of x times q of x plus r of x. So this is that polynomial form where you have d of x times your quotient, so divisor times quotient plus the remainder. Now, like it says, f of x in the division algorithm, that's the dividend, and d of x is the divisor if r of x equals 0. So if there isn't a remainder, because the remainder was 0, we say that d of x divides evenly into f of x. And those are the special ones. And as we start going through that list of objectives today, we should realize, hey, we're really starting to talk about finding all of the zeros, and that's what's going on here. The summary statement in the division algorithm will sometimes be written in fraction form. So this is what we started with today, where we had f of x and we divided it by d of x, dividend divided by divisor, and we got a quotient, and then we wrote that little fraction at the end, r of x over d of x. So that one is fraction form. For instance, to summarize what we just did, here it is with some nice type. Here's the exact same problem that we did with long division, and here's the quotient plus the remainder, 3 over 3x plus 2. So just two different forms, two different ways to write your answer. Example 1 says using polynomial long division, use long division to find the quotient and the remainder when 2x to the fourth minus x to the third minus 2 is divided by 2x squared plus x plus 1. Write a summary statement in both polynomial and fraction form. Well, we'll start at the beginning. We have some division to do here. So, as we start to write this out, we realize this one is missing some stuff. It doesn't have a squared term, and it doesn't have an x to the first term. It doesn't have a linear term in there. So what should we do about that? Well, for most people, you can keep more organized if whenever something is missing, you put it in as a 0. So if we have 2x to the fourth minus x to the third, and then it makes the jump down to minus 2, we should put in plus 0x squared plus 0x and minus 2, because usually it's the spacing that messes people up with this. And we're dividing that by 2x squared plus x plus 1. Now, we go through the same process. Pardon me. I have a 2x squared plus x plus 1. And what I want is to just focus on the first term. I want to get rid of 2x to the fourth. That means I need to get 2x to the fourth in the first position. Well, I already have a 2, but I only have an x squared. So that would mean I need a couple more x's. So I'm going to multiply that by x squared. And that will give me 2x to the fourth plus x cubed plus x squared. And that's why I mentioned earlier having those 0 in there. Having that 0 in there is going to help with organization. And then we don't want to forget, change the signs. Let's see what happens. 2x to the fourth minus 2x to the fourth is gone. That means my x squared was good. I'm going to put my x squared up here, lined up with all the other x squareds vertically. And then I have negative x cubed minus x cubed, which would be minus 2x cubed. 0x squared minus an x squared would be minus x squared. And then, like we usually do, we'll bring down that next term, which is a 0x. Starting again, 2x squared plus x plus 1. And I realize, well, this time I need negative 2x cubed. So I'm going to need a negative. And I'm going to need another x. So that's going to be multiplied now by negative x. Negative 2x cubed minus x squared minus x. Again, I want to change the signs so I don't lose track of that subtraction. And negative 2x cubed plus 2x cubed is gone, so I'm going to put my little minus x up there above the other x's. And negative x squared plus x squared, that's going to be 0. And then we have 0x plus x, which is x. And like I said, just do this like normal division. You bring down the next term. But then I realize 2x squared plus x plus 1, how am I going to get 2x squared to be x? I mean, that's not going to happen unless I'm using some weirdo fractions and stuff, and we're not supposed to do that. We're just supposed to use nice integers here. So that means I'm seeing right now my remainder piece right there. So my remainder is going to be a little bit messier this time, plus x minus 2 over what I divided by, which is 2x squared plus x plus 1. And we've got it. Now, we're not done yet, but I wanted to show you the picture here of what we see with this. And this is the graph of 2x to the fourth minus x cubed minus 2, which is our dividend here. And then 2x squared plus x plus 1 times the quantity x squared minus x plus x minus 2. Now, if you're looking at that and you're saying, but Cedarholm, there's only one graph, you're absolutely right. Because if we did the math right, they should match perfectly. They should be the same thing. So now we need to write our two answers. And normally, Probably wouldn't even write down fraction form, I'd just write down the answer, but I want you to see the difference between our fraction form and then our polynomial form. So our fraction form is what we just found. Right there. X squared minus x plus the quantity x minus 2 over the quantity 2x squared plus x plus 1. But in polynomial form, just remember, this is how we would check it. Pardon me, I haven't talked a lot over Thanksgiving break, so I'm having frog issues here. And that would be if we took 2x squared plus x plus 1, which is our divisor, times our quotient, and added our remainder. And like I said before, that's actually how we would check it and make sure that it was right. You know, if we had time at the end of a test to go back and check and make sure everything is working. So the fraction form is the one with the fraction. The polynomial form is the one that would be the feeling of, hey, we're going to check our answer here and make sure all of this works. So we've sure hit that long division objective really hard so far. And again, there is a way to check this with your graphing calculator. That's what all of this is about right here. And basically, if you want to put this little box in your notes with a quick little sketch, just remember they have to graph exactly the same. Otherwise, you messed up. If they don't graph as what appears to be one graph, then you made a mistake. All right, so I'll give you a chance to get that down on there. And again, we're using long division and the division algorithm today. We're going to be talking about the remainder and factor theorems. And we're going to use the rational zero theorems. Probably won't get to those upper and lower bounds. So unless somebody unmutes and tells me they need more time, I'm going to go ahead and move on. An important case of the division algorithm occurs when the divisor is of the form d of k equals x minus k. That makes it a linear factor. And that's because this is an x to the first, and x to the first graph as lines. So like it says, d of x is x to the first minus k, where k is a real number. Because the degree of d of x equals x minus k is 1, the remainder is a real number. Now, this brings us to other part of our objective here, with just talking about the remainder theorem. And here's what it says. F of x equals x minus k is now what we're dividing by. Here's our quotient, and then we add the remainder. Well, that's not any different than what we were doing before, except if we have x minus k, and x minus k is actually a 0 of the polynomial, that would mean x equals k. For instance, let me show you here. If we have x minus 3, that means that k is 3 because the minus was already part of that. So if we put a 3 in here for x, 3 minus 3 will give us 0. And that's what's taking place right here. So if we put a 0 in here, 0 times anything is 0, and we're just going to get the remainder. Now what that means is, if they give us a 0, and they tell us, hey, this is a 0 of this function, then what we can do to find the remainder is just go ahead and put that 0 in, as we did right here. Substitute that in there. So the remainder theorem is what we're really talking about. So if f of k equals r, that's your remainder. And if all you're interested in is, does this have a remainder or not? Then, if the polynomial f of x is divided by x minus k, then the remainder is f of k. This enables us to find the remainder of a polynomial when it is divisible by x minus k. Again, that's a special case with a linear factor. So here's what it's saying. Find the remainder when f of x equals 3x squared plus 7x minus 20 is divided by these. And the first thing I think is, First thing I was thinking was I can't use green. I have to remember that. That x minus k is how these are written. So what they're saying is if this is just the remainder that we want, all I need to know is what's going to happen if I put a 2 in here. So I'm going to put a 2 in, and I'm going to see what I get for remainder. 3 times 2 squared plus 7 times 2 minus 20. Well, you follow the order of operations. You have to do powers first. 2 squared is 4. So 3 times 4 plus 7 times 2 minus 20. Multiply and divide from left to right. 12 plus 14 minus 20. And then we'd go ahead and add and subtract from left to right. So 12 plus 14 would be 26, minus 20 is 6. So this doesn't divide in evenly. It comes out with a remainder. It will have a remainder of 6. And if that's all we wanted to know, then that's all we have to do. So I look at B, and I realize, oh, that must have been a negative 1 that they put in there because it somehow became x plus 1. So it must have been x minus a negative 1. So what I really have to do is find f of negative 1. And I want to see, does it have a remainder? So 3 times negative 1 squared plus 7 times negative 1 minus 20. Same thing again, follow those order of operations. So negative 1 squared is 1. Then we have 3 times 1 is 3, 7 times negative 1 is negative 7, 3 minus 7 is negative 4, minus 20, negative 24. So that one also has a remainder. You know, that tells us that's not a 0. Well, let's check out C. Again, I see that linear factor, so I'm thinking x minus k. Oh, it must have been a negative 4 because it became a plus 4. So f of negative 4 just doing the substitution there, putting the negative 4 in for the x's. Follow the order of operations. Negative 4 squared is 16. And then multiply and divide from left to right. 3 times 16 is 48, minus 28, minus 20. 48 minus 28 is going to give us 20, and 20 minus 20 is 0. Now that means this one is special. That tells me that x plus 4 divided into 3x squared plus 7x minus 20 perfectly, evenly, no remainder. That also tells me that this is a 0. So we're connecting all the information that we know about graphs so far, and this is adding another new piece to it where we're going to know where it crosses the x-axis by finding those zeros. So why is this important and helpful? If we can find a remainder of 0, it means that that factor x minus k divides evenly into our polynomial. This indicates that k is a solution, and if it's a solution, it's also an x-intercept of the graph of the polynomial. So down here in the blue it says, using the table feature of the calculator helps us to find the remainders of several division problems at once. Because what the calculator is doing is it's putting all of these little x values here into 3x squared plus 7x minus 20. And the ones that we just did up there, oh, I don't want to scroll back and show you that. Let's see, it was 2. I'm just going to use my... There's the 2 that gave us a remainder of 6, just using my binder here to read those off instead of scrolling back up and down. That would be annoying if I were you. And then negative 1 gave us negative 24. And then there was the really important one, which says something more than just, hey, if you put this number in, here's your remainder. And that is that a negative 4 would give us a 0. And this is really easy to do on your calculator. All you do is go ahead and put in the 3x squared plus 7x minus 20, and you'll notice that's the only one I have turned on right now because that's darkened. Second table, there it is. So that allows you to find a lot of remainders at one time. But again, the one that's going to be significant for us is when we find those remainders of 0, because that divides into it evenly. That's a linear factor of our polynomial. All right, so my little record stuff is over the top of this. I wanted to show you this piece. Here's what it's saying is, there's our 3x squared plus 7x minus 20, showing those remainders when you divide by x minus k. That's going to help us out. We can use the table to find some that we think are pretty obvious zeros and then work from there. Now, the factor theorem. Well, this is just what we were talking about. If it is a 0, so if the remainder, f of k, is 0, a polynomial function has a linear factor of x minus k. It divided into it evenly, so there's our linear factor. And like it says, using the ideas of the factor theorem, we can take a new look at that last example, because we now know that we have a factor of x plus 4. So using long division, we could say, all right, this is 3x squared. I have an x plus 4. I'm going to need a 3, and I'm going to need another x to make this work. So that would be 3x squared plus 12x. Change the signs. 3x squared minus 3x squared did exactly what we wanted, so let's put that little 3x right up here. And then we have 7x minus 12x for minus 5x minus 20, bringing down that next term. Start over here again. I need a negative 5x, so I'm going to multiply this by negative 5, and that will give me negative 5x minus 20. Change the signs. The negative 5 worked, and I get 3x minus 5. But what I've also just found is the other factor for this, because I now know x plus 4, that quantity, times the quantity 3x minus 5 will give me 3x squared plus 7x minus 20. So this is kind of, and not that any of you would need this, but it's an educated cheat for factoring. If you know that you have a 0 and you're a person that has struggled with factoring, this is a way around it. And this would actually be the fraction form and the polynomial form, because this one had a remainder of 0 in it when we went through. So this process can be quite helpful for polynomials of degree 3 or higher. We can find factors, zeros, and x-intercepts. So having the knowledge that, hey, there's a 0 out there somewhere should help us with all of those. And this big box here has all those connections for us. Fundamental connections for polynomial functions. For a polynomial function f and a real number k, the following statements are equivalent. X equals k is a solution. Solutions are sometimes also known as roots of the equation, f of x equals 0. K is a 0 of the function f. If you put k into the function for x, you're going to get 0. K is an x-intercept of the graph. So now we're connecting it with the visual. And then x minus k is a factor of f of x, which, like I said, can be used as kind of an educated cheat for factoring. But it definitely is more work than it's worth if you know what you're doing when you're factoring. So x minus k as a factor is a special case. And it says, do you remember another method to find both quotients and remainders without having to use long division? Well, this is special. Not all polynomials will have linear factors. And so we have to recognize, hey, there's something significant about the fact that this is a little linear factor here. And what that does is it creates a situation where we can use synthetic division. So synthetic really comes from, if you look at the proof for synthetic, it comes from a nested procedure. But this is just kind of breaking it down and saying, hey, if you just look at the numbers here, look at how this makes sense. Here was our long division. Now, if we look at 2, 3, and 4, which were the numbers that we would use for our coefficients up here at the top, and just the negative 3 from x minus 3, we would see that we get these numbers, which are really hard to see in this color right here, negative 6, negative 9, and negative 12. And then somebody notices the pattern, hey, if I start multiplying outside the box and adding inside the box, I get the exact same answer that I had before. And so this takes us all the way to synthetic division, where we say, all right, I've got a 0 of the divisor, and I want to see what do I get if I divide by, in this case, x minus 3, which would give us a 3 for synthetic. Now, this isn't the way you guys are used to seeing this. In the Algebra 2 book, it would look like this. And it's up to you whether or not you want to stick with the Algebra 2 book way or if you want to use the new way that you see here where we have this little box up in the front. But when you first learn this, this symbolism is actually easier for students because it kind of looks like an upside down division symbol. And if you think of it as a box, then the rules for synthetic would be if you're inside the box, you add. And if you're outside the box, you multiply. And synthetic division is a really quick and easy way. Most of the time you don't even have to use a calculator to do any of the math that's used as you're doing synthetic. But what we do is we start with the leading coefficient, which would have been the 2, and we bring it down outside the box. So there's your first step. Bring it down. Now you're outside the box, and you have to multiply. And you think, well, what do I multiply by? The only other number that's outside the box, the 3. So 2 times 3 is 6, and then we have to go inside the box because we have to oscillate from outside to inside, outside to inside. Now we're inside the box, and we add. We're back outside the box. We multiply again by the 3, and we write our answer inside the box. And then negative 5 plus 9 is 4. We're outside the box. We multiply by 3, and we're inside the box, and we add. And we get a remainder of 0. Now, if we want to know what our answer is, we have to start from the right and say, well, there's no remainder. This will be the constant, this will be the x, and this will be the x squared. So, x minus 3 divides into the polynomial 2x cubed minus 3x squared minus 5x minus 12 perfectly, and we get a quotient of 2x squared plus 3x plus 4. And this is truly math magic. You know, we're taking all of the x's out and using this. And it always happens that after we learn synthetic, everybody likes synthetic, and it goes so much faster and easier. It's like, why can't we do this for everything? Because we can only use math magic when we have a linear factor of the form x minus k. So that means if they want us to do some division with something like 2x plus 1, we can't use synthetic for that. We have to use long division. It has to be a linear factor of the form x minus k to do synthetic. So back to our objectives here. We want to know how to do synthetic division. That was one of the objectives today. So it says, let's go ahead and do this division using synthetic division and then write a summary statement in fraction form. You know, what did we get? So there's my divisor, x minus 3. And I realize if it's x minus k or x minus h, it doesn't make any difference what the variable is. What matters is I only want the 3 because that's what I want to do the division with. And then we grab those coefficients for each of the terms that we see in our dividend, and what we want to do is if there's anything that's missing, in fact you have to with synthetic, if anything is missing you must put in the zeros. So what I wrote down over there is if anything is missing, use a 0 as a placeholder, even if the constant is missing. So you don't have that end number. You have to put a 0 in there. That's the only way synthetic will work. So we make sure it's in standard form, which means highest power on down, 3, 2, 1, 0. We make sure there's nothing missing, had something in all those places, and then we go ahead. And I already did this on the other page, but we'll go ahead and do it again so that you can get some repetition at this. Bring down the 2, the leading coefficient. Outside the box, multiply, and write your answer inside the box. You're inside the box, add. Outside the box, multiply. Inside the box, add. Outside the box, multiply. Inside the box, add. And like it said, you'd write your summary statement in fraction form. So you start over here, constant remainder x squared, 2x squared plus 3x plus 4. And this one did not have a remainder, so I don't need to write anything behind it. It's 2x squared plus 3x plus 4. That is our answer. Now, obviously, we'd love to use synthetic all of the time, and I talked about this on the last page. The reason that we can't is because it has to be of the form x minus k, and that means we can't just throw out long division. We'd love to. It's like I said before, it's not difficult. It just is time consuming, and you have to be very careful as you go through not to lose anything. So we can't use synthetic all the time. That's the major point, and that means we still have to know about long division. We have to. So 2 polynomials are given. Use either synthetic or long division to divide p of x by d of x and express your answer in both ways, whether or not we're going to do it in polynomial form or in fraction form. So this one has x cubed plus 4x squared minus 6x plus 1, and we want to divide by x minus 1. And I immediately recognize that is a linear factor. So I can do this one with synthetic. So that would be the best way to do this problem. And again, that's what we're about at the pre-calculus level is what's the best way. So I'm going to do this one synthetically. Remember, though, that it's going to be a positive 1 because we just want to use k from this. And then I double check, is this in standard form? 3, 2, 1, 0. The powers are in standard form. Nothing's missing, so I'm not going to need any zeros for this. 1x cubed, 4x squared, minus 6x, and a 1. I bring down my leading coefficient, and then I start the process of multiplying outside the box, going inside the box and adding, multiplying outside the box, going inside the box and adding, multiplying outside the box, in the box, and adding. And notice I put a little rectangle around that last number there. And that's not, so that most of the time, if somebody makes a mistake on this, what they're doing is they're forgetting that this is going to be the remainder, and they start writing it as if it were the constant. If you make that box, then you'll remember, oh yeah, that's the remainder piece here. So remainder constant x squared plus 5x minus 1. So that was our answer. Now that's in fraction form because we did not have a remainder. And for polynomial form, what we would have to do is say, so if I took x minus 1 times x squared plus 5x minus 1, I would get back to the original answer. So this is fraction form, and this is polynomial form right here. Now, for fraction form, every once in a while somebody wants to put plus 0 over x minus 1. We don't need that, and if we don't need it, it shouldn't be there. So we would simplify that off and say we don't need that. It's not important to this problem. Make sure all that's written on there for anybody looking at the notes later. But that one worked out really nice and quick because it was synthetic. I go to B. P of x equals 4x cubed plus 7x plus 9. My divisor this time is 2x plus 1. Rats! I can't use synthetic for this one. And that's because of that 2 out in front of there. So what I have to do is long division with this one. So 2x plus 1 divided into 4x cubed. And I notice there's no x squared, so I'm going to put a 0x squared in there. Plus 7x plus 9. And then we change our thinking because, again, this one's going to be long division. So now I think, well, what do I multiply 2x by to get 4x cubed? I'm going to need a 2, and I'm going to need an x squared. So that will give me, change colors here, 4x cubed plus 2x squared. I'm going to go ahead and change those signs and add those together, and it did what it was supposed to do. I got rid of the 4x cubed, so 2x squared is going to go up here as part of my quotient. And then when we do our addition or subtraction here of those polynomials, we get negative 2x squared. I have to bring down the next term. And I start over. 2x plus 1. I need it to be negative 2x squared, so I'm going to need a negative x to make this work. So that'll be negative 2x squared, which is perfect, minus x. Again, we have to change the signs and add. So negative 2x squared plus 2x squared did exactly what it should. I'm going to put my negative x up there. 7x plus x is 8x. Bring down the last term there, which is the 9. And I have a 2x plus 1. I need to match up with that 8x, so I'm going to multiply by 4. And change the signs. 8x minus 8x, the 4 did its job. And then 9 minus 4 is 5. And that's going to be my remainder. So, in fraction form, it will be 2x squared minus x plus 4 plus 5 over 2x plus 1. And then, oh, I don't like that that's kind of sideways there. In polynomial form, we would get 2x plus 1, that's our divisor, times 2x squared minus x plus 4, and then add that little remainder of 5, because again, that's as if we were checking it. So fraction form and polynomial form. So, since I'm going to run out of time here, this is probably the best place to stop, which means we did not get to everything that you need to do the 2-4 day 1 assignment. You can get a good start on it, but you're not going to be able to finish it up because we didn't get to talking about all of the zeros here yet. We got a good start, and yeah, you might remember quite a bit from last year. But 1 through 26, go through what you can. We've talked about this before. If you get to a problem and you're like, nah, I want to wait and see an example in class, I'll wait until Cedar Home does one of those. That's perfectly fine. So section 2-4 day 1, page 205, number 1 through 26. Lots of objectives in here, but we have 3 days scheduled, so we'll get there. It's just going to take us a bit.